Yes, sir. We can start, right, sir?
Yes, Adil. Please begin.
Okay. Yes, sir. Sure. I mean, before we begin, I think I should give some instructions. I request all the students to keep your mic and camera turned off during the session. Also, please avoid sharing your screen while the session is in progress. Or if you have any questions or doubts, feel free to type them in the chat box during any time in the during the session. And but please mention your name and class along with your question, and we will take those questions up during the Q&A session. And also keep your questions in English. By that, I think we can get into the official introduction. So I am Adil Krishna, a student fellow of US Space Club, and it's my pleasure to welcome you all to the 18th session of our webinar series. US Space Club is a registered space tutor of ISRO, and this webinar series began more than 5 years ago during the pandemic, during the COVID pandemic. When we started, we've been holding sessions every Saturday, but now we continue the tradition every second Saturday because over the years we have grown and launched many other initiatives like a Sky Safari, an online sky watching program. The Cosmos is there. It's a platform for curious young minds and STEM with mentors and students of your Space Club. And also there is this Model Space Startup Challenge. Second edition is going to be happening in next week. And it's our flagship event. It's for high school and higher secondary students. It's a startup pitching challenge. So coming back to the webinars, on this occasion, I would like to share my heartfelt thanks to those who initiated this webinar journey, our team lead Varun K, and our mentors Ike Kuti sir and Jairam sir, of course Sejil sir, who have been moderating every single session we had so far. And this platform, this webinar platform has graced many speakers from many students like ISRO, VSSE, IAA, then IAST is there, NITs, IITs, MITs, and ISIS, and many other organizations are also there. And today we are really honored to have with us Professor Mousumi from IAA, and it's also quite special to note that this entire webinar series was launched 5 years ago with a talk by another veteran from IAA itself, Professor Jayant Murthy sir, on the expansion of universe. And today, Mousumi will be taking us on a deep dive into the nuclear activity in galaxies. And we're all very excited to learn from her. And also, I am very happy to be here because I am currently doing an internship under ma'am. And a warm welcome to you, Mousumi ma'am. And I also take this moment to thank yes, sir. I also take this moment to thank and warmly welcome all the veterans and senior guests who have joined us today. Your presence means a lot to us. Now, I think without any further delay, I would like to invite Sujit sir to take over and moderate the session. Over to you, sir.
Okay, thank you, Adil, and proud of you. And be connected with the Institute of Astrophysics as an intern there. We are so proud. And the US Space Club has successfully completed about to complete 80 insightful webinars, bringing together scientists, educators, and students to discuss diverse aspects of space science and astronomy. These webinars have played a pivotal role in fostering scientific temper, awareness, and curiosity among the student community and general public. We are proud to say that this journey began on 23rd of 2020 during the time of pandemic. The first webinar delivered by Dr. Jayant Murthy, Senior Professor of that great institute, a leading expert in ultraviolet astronomy and space instrumentation. Today, we have a great Indian scientist on this from the astrophysics, Professor Mousumi Das. She is an exagalactic astronomer working at the Institute of Astrophysics in Bangalore. She works on various topics related to the galaxies, including star formation, galaxy merger, dark matter in low luminosity galaxies, and nuclear activities and galaxies. She uses both numerical methods and multi-wavelength observation to understand galaxy dynamics and evolutions. And she holds a PhD in physics. From Department of Indian Institute of Science, and her academic background is complemented by active involvement in several renowned scientific communities. She is a member of Astronomical Society of India and contributes to the TMT, International Science Development Team. And we are proud to have such an eminent scientist from a eminent institute of India. And our students now grown up to that level. Adil was started this journey from he was a kid in 7th standard. Now he's reached there. We are proud of this team, and we are proud of the activities. Our founder, Mr. E.K. Kuti, former director ISRO, we are proud of him. With his guidance, with his guiding light, we are moving together with the scientists, teachers, students, and the common people, connecting all together. We started at the time of pandemic. Still, we are wondering, we are completing 5 years of these activities for our children. And sure, our children get motivated. Some more people are coming back to guided with seniors there, and so delighted to have having time with you, ma'am. And I invite all the veteran scientists of ISRO, teachers, students, and our distinguished guest, Professor Mousumi Das, to interact with our children. Welcome, ma'am.
Thank you very much. Am I clear?
Yes, ma'am. Your audio and video are very clear.
Okay. So shall I share my slides now? Oh, okay. I'll just share my slides. Oh, sorry. I don't know what happened there. This one. Okay. Can you see my slides? It's a PDF. Okay. Okay. Is it in full screen mode? It's full screen? Oh, it is moving.
Yes, I mean, there's a glitch. It's going full screen and coming back. It's now it's
fixed. Okay. Okay. I have to just keep my cursor on it, I think. Some last meeting, they told me this. I have to keep moving my cursor. So maybe I should start now. Shall I start giving my talk? Okay, so before I start my talk, I just want to thank you all for inviting me to give this webinar. It's a great pleasure, great honor also to be giving this talk among so many students and so many faculty. So I'm going to talk about galaxies and their nuclei, their nuclear activity, and I'm going to give it at a slightly technical level, because I know all of you are, you have background in science. So I'm going to give it at a slightly technical level. I'm going to talk about the different types of galaxies, a little bit about stars, but also about galaxies. I'll talk about the different telescopes that in India we use to study galaxies and that I have been using. Then I will go on to the sciences, the science of understanding galaxies. And apart from, the main topic, the galaxies and their nuclei, I will also give some physics background about galaxies, because I think it's important for us to know, because, we are all having science background, and, we can classify galaxies based on their physics, on their kinematics, and I have always tried to emphasize this in my talks. Then I'll talk about the centers of galaxies. I know students love hearing about black holes, but it's not all just black holes. The centers of galaxies also have a lot of star formation. So I will also hint upon that as well. So I'm going to give my talk, but I think at regular intervals I can stop and I can take questions as well, because if the questions are at the end, I think it may get a little boring for the students. So I'm going to start right at the beginning, the stars. Stars are the basic building blocks of galaxies. This is something that all of you know, I'm sure, but I just wanted to go back to it. The stars give out, it is jumping a bit. I don't know why, sorry. Okay, sorry. Okay, so stars, is it stable now, Adil? It's okay, no?
It's not stable, ma'am.
It's not stable? Okay, let me just put it here. Is it stable now? Is it stable now? Okay, so stars are the building blocks of galaxies. Stars are of different categories. I think that most students know. The most massive stars are the hottest stars. And so when we look at galaxies, the starlight, the light coming from the stars makes them bright. But that light can be of different colors. It can be dominated by the blue. It can be a little reddish. And that tells us a lot about the stellar content of the galaxies. Because galaxies, when they are dominated by young, massive stars, and here it's the O and the B, and perhaps a little bit of the A-type stars, the OB type stars, then the galaxies appear blue. When the stellar content is dominated by the red stars, the older stars, and the less massive stars, then the galaxies appear slightly reddish. So the stellar classes and the stellar content of galaxies also tells us a lot about what is the color of the galaxy. And that's one way in which we try to understand the stellar content, the photometric emission coming from the galaxies. Now, stars give out energy because their nuclear fuel, burning of their nuclear fuel, the most massive star, it burns the fastest. In fact, the time of evolution of a star is inversely proportional to their mass. So that means the most massive stars evolve the fastest. So the OB stars have the shortest lifetimes, whereas stars like our sun, they are, it's a G-type star, so it's a low mass star. Over here, you can see it evolves a lot more slowly. So this means that when we look at galaxies, we are actually, the light is dominated by the old stars, the stars which are having not only age high, but also mass is low. Because in any galaxy, when the stars are formed, there are always more low mass stars formed compared to the high mass stars. Now, galaxies are composed of a lot of stars, and you know the numbers in astronomy are always much larger than in any other field of science. So galaxies are composed of 10 to the power 3 to 10 to the power 12 stars. The smallest galaxies, which are called the dwarf galaxies, can have only about maybe a few thousand stars. These are the really small satellite galaxies which surround the major large galaxies like our galaxy, the Milky Way. But some of the really big elliptical galaxies have 10 to the power 11 or 10 to the power 12 stars. Our galaxy has about 10 to the power 11 stars, we think. Now, when we look at galaxies in a field like the one shown here on the right, which is the JWST look at a deep field, you can see that the galaxies, there are a whole types, there are many types of galaxies. There are these kind of cloudy looking structures. Those are the elliptical galaxies. But you can also clearly see that some of them are disk-like galaxies, like the one over here. Another interesting fact is that when you look at the deep field, like the one shown here, you can see several arcs. And those arcs are gravitationally lensed structures. So when you look at a deep field from a powerful telescope like HST or the JWST, you'll not only see galaxies, but you'll see also these arc-like structures. Now, this is just what we see from the electromagnetic emission from the galaxies. But there's a lot of components of galaxies which you cannot see easily with the telescopes, these optical telescopes or near-infrared telescopes like JWST. And those are dark matter, dark energy, neutrinos, then the cosmic wave background. There are many components of the universe like this which you cannot see in a deep field. But the main thing that we see is the electromagnetic emission. Now, I always start my lecture with this image or a similar image because I want you all to remember that we can all look at our galaxy, our galactic plane. Our galaxy is actually commonly referred to as the Milky Way. And that's because if you look at a night sky, you see a long band of light going across the sky. And this is actually the galactic plane of our galaxy, the Milky Way. Now, the reason why we can see this line or this kind of band stretching across the sky is because our solar system is at a slightly angle of about 23 degrees with respect to the galactic plane. And because of that, we are kind of a little bit above the plane. So we can see the galactic plane. If we were residing inside our solar system, if our solar system had an orbital plane which was inside the Milky Way plane, we would not have been able to see this band of light across. Now, Galileo was the first one who realized that this band of light that we see in the night sky is actually composed of stars. And in 1610, when he made his telescope, then he was actually able to see that these were actually stars. So this is a historical slide, but I just wanted to show you because the next time you go to a very open space, please take a look. Somewhere in there is the center of our galaxy. Now, galaxies, as most of you know, are of two types. They are spiral galaxies or elliptical galaxies. A spiral galaxy is basically, yes?
The slide is a bit unstable right now.
Oh, is it okay now?
Yes,
move my cursor.
Okay.
Okay. I'll try to keep moving my cursor. So spiral galaxies or disk galaxies, they are basically composed of a disk of stars moving in circular orbits about the center. And so you can imagine that it's like a thali, it's like a plate which has a finite thickness in which stars are moving about the center. And the stars move in a particular way. They have what is called sheared motion or differential velocities, which means that a little bit outside the bulge, the center of the galaxy, the stars move with V is equals to R omega, but omega is a function of R. So as you go further and further out, the different layers are moving at different angular speed. So this is very important because first of all, it gives rise to what we call the rotation curve of galaxies. And secondly, it also gives rise to very often to the spiral structure. Now here in this image, you can see on the left, these two images of spiral galaxies, there are these very distinct spiral arms. Now, a lot of the evolution of these spiral arms is dominated by the differential rotation. Now, elliptical galaxies have a very different kind of kinematics. As you can see, they appear to be in an ellipsoid, and the stars are moving in orbits. These orbits are often loop orbits or boxy orbits. So they trace a kind of ellipsoidal structure, but the whole galaxy as such is having a nucleus, a center. So it's a symmetric structure, but it's a three-dimensional ellipsoid, whereas the spiral galaxies are two-dimensional disk structures. So this is a very simple introduction to the differences between the galaxies. But to understand that further, I think we have to understand what galaxies are made of. Galaxies are made up of stars, of course, but they are also, the spiral galaxies are made up of interstellar gas, ionized gas and neutral gas. They're also made up of interstellar dust, cosmic ray particles, and dark matter. So cosmic ray particles and dark matter I will not talk about in this talk, but cosmic ray particles are charged particles such as electrons, positrons, alpha particles, and they come mainly from the energetic nuclei of galaxies. And dark matter is matter that we can detect from its gravitational effect, but we cannot actually see. Now, the gas is of basically three types. It can be neutral hydrogen, and we commonly call it as H1. It can be molecular hydrogen and it can be ionized gas. Now, most of the universe, you have to remember, is composed of hydrogen. That is the main component. About 10% of our universe by weight is in helium, and a few percent is made up of other particles all over the periodic table, which have come from supernova explosions and other processes of recycling materials. Now, the ionized gas mainly comes from the emission from the massive stars, the O and B type stars. It also comes from the stellar winds from the less massive stars. The elliptical galaxies, however, are very different. They do not have any cold gas. When I say cold gas, it's not really that cold, but it is mainly neutral. So molecular hydrogen, neutral hydrogen gas is usually absent in elliptical galaxies. Instead, there is hot ionized gas along with the stars and the dark matter. So the composition of the two types of galaxies is very different. Now, this is a slide which I don't always show, but you are all having science background. The kinematic difference between ellipticals and spirals is very important, and it's a good way to understand why they are so different. Now, in disk galaxies or spiral galaxies, the gravitational force which tries to make the system collapse onto itself, that is opposed by the centrifugal force. So the equilibrium for the equilibrium equation for the system is simply the one we learned in class 12, GMM by R squared is equals to V squared by R. And I have just showed it over here. So that means that this equation, if we assume that the dark matter halo is spherical, then this simple equation will give us the dynamical mass of the galaxy within a radius r. So mr is equals to v squared r by g. Now, in an elliptical galaxy, the equilibrium, it's an elliptical system. It's not a disk system. So the equilibrium is much more different. It is the gravitational force is balanced by the random motion of the stars. Now, it's not totally random, the motion of the stars, because there is stellar orbits, such as loop orbits, boxy orbits, which kind of define a structure, an ellipsoidal structure for elliptical galaxies. Now, but what this motion does is it creates a pressure, a kinematic pressure, and this pressure supports the elliptical galaxy from collapse. Now, the equilibrium equation that is used to describe this is called the virial equation. And some of you might be knowing, for gravitating systems where there is a 1 by r squared force, the equilibrium is given by 2t plus v, where t is the sum of the kinetic energy of the stars and v is the sum of their potential energy. So there is a very strong difference, kinematic difference between spiral galaxies and elliptical galaxies. And this kinematic difference is reflected in their shape. The spiral galaxies are disk galaxies, whereas the elliptical galaxies are three-dimensional structures, and they appear as ellipsoids. Are there any questions before I start discussing the galaxies in detail?
Ma'am, I think we can continue the session till the end, and we will have a Q&A session at the end. That's what we usually do.
Okay, fine. I'll continue then. Okay. So let me go a little fast because I think it's a lot of time has already gone by. Spiral galaxies are made up of disks embedded in dark matter halos. We usually think that the dark matter halos are spherical, but now research has shown that they can have different shapes. Now, this disk, the disk is surrounded by also a population of stars, which are first of all in globular clusters and also in just isolated stars. And the disk is often composed of two parts. One is the thin disk, which supports all the newly formed stars, and a thick disk, which is made up of the old stars. So this is the general picture, the idea we have for a disk galaxy. And our galaxy is a very good example of this structure. The elliptical galaxies, as I mentioned earlier, are ellipsoidal in shapes, and they are supported by the random motion of the stars. And they have very often, they have very strong ionized gas halos. So they often appear very boring. In fact, when I was a student, I thought the elliptical galaxies are kind of boring structures. But nowadays, we know, in the last 20 years, we know that they host the most massive black holes. And those black holes, when matter falls onto them, basically when they start accreting, they give out a lot of energy. And sometimes they give out jets as well. So there is a lot of energetic phenomena that is associated with elliptical galaxies, which you cannot really make out when you look at their simple image, optical image. Now that I've just told you about the two types of galaxies and how they are different kinematically as well, I will also just mention about the Hubble sequence. Now the Hubble sequence, which some of you might know, is like a tuning fork, which means that there is a kind of a division at a junction here. Now at this junction here, I'm sorry, I'm not sure why my screen keeps flipping like this. Very sorry. Is it stable now, Adil?
Yes, madam, it's stable.
Okay. So the Hubble sequence is composed of elliptical galaxies on the left-hand side, which I'm showing here. And it is composed of spiral galaxies on the right-hand side. Now, on the left-hand side, you can see that it's not just elliptical E, but there's a number associated, E0, 3, 2, and so on. And it goes as far as E7. So this number actually means the ratio of the axis, B by A, 10 times 1 minus B by A. So it's kind of telling you how compact or flat the ellipsoidal galaxy is. And you can see here that it does not go beyond E7. And that's because if the system becomes too flat, then it becomes unstable. There is a instability called the fire hose instability, which will make it become unstable, and the stellar system will become again fat or become more elliptical. Now on the right-hand side are the spiral galaxies, and the spiral galaxies or disk galaxies are of two types. One type has a bar in the center, which is below, and the other type does not have a bar in the center. And you can see that they vary along this tuning fork, the galaxy shape, and they vary in two ways. First of all, the bulge becomes from large to small as you go from left to right. The second way in which the system changes is that the spiral arms become from very tightly wound in the early type spirals to very loosely wound in the later type spirals. So this is just a very simple idea about the different types of spiral galaxies as they are shown on the Hubble sequence. One thing that you have to remember, I always tell the students, is that there is no real evolution along the Hubble sequence. It is just a classification scheme. To have the evolution of the galaxies, you need star formation and often the mergers of galaxies. Now I'm going to talk about what kind of telescopes that we use. Basically, I think you can say now that there are two types of telescopes: the ground-based observations, which uses multi-wavelength telescopes situated in different parts of the world. And the second is the space-based observations. Now, the ground-based observations, the advantage they have is that they are not so expensive. If you have a space-based observation, a telescope such as the Hubble telescope or our own AstroSat telescope, Indian telescope, costs a lot of money, and it costs years and years of planning, whereas a ground telescope does not cost that much. But a ground-based telescope suffers from a lot of problems such as atmospheric problems. The atmosphere scatters or just absorbs a lot of the light coming from the galaxies and basically from the universe. So let me just go quickly through. Before I start showing you a few of the telescopes that are in India, I'll just show you the whole list. I mean, this is just actually the electromagnetic spectrum. But I just wanted to remind you that there is gamma ray telescopes as well as X-ray, UV, all the way to radio astronomy telescopes. So right now in India, in IIA, we have two very good telescopes. One is the Hanley telescope. Another optical telescope is the one we have in Kavalur. We are also very proud in India. We have one of the best radio telescopes in the world called the GMRT. This is located in Pune, 1 hour from Pune, and it specializes in low frequency radio observations. So frequencies that go from 150 megahertz all the way to a gigahertz. And the telescopes over here, the Hanley telescope, it observes both in the optical as well as in the near infrared. There are also many other telescopes, but let me just tell you a little bit about AstroSat because I also use AstroSat data. It's India's first multi-wavelength space observatory. There were some other space telescopes which were launched in the 70s, but such as Aryabhatta, but they did not have multi-wavelength and their data was not used by a large population of people. Whereas AstroSat, which started giving data in 2017, is used by the international community as well as scientists in India. It has a UV telescope called the UVIT. It has also X-ray telescopes. One is the SXT and the other is the CZTI. Now, all these instruments together can help us study various facets of the universe, stars, galaxies, and even very high redshift observations. It's also very important for studying time variable observations because I would say in the last decade, the transient sky has become very, very important because it offers a mean to understanding, first of all, gravitational waves, but also to understand the various phenomena. There are things like fast radio bursts, which we still don't understand. So the AstroSat telescope has been very, very successful and very important, not just for Indian scientists, but also for international scientists. It was launched by ISRO. Now, in India, in the last decade, we have also started having international collaborations. I think one of them is called the 30-meter telescope. And this telescope, IIA is part of this telescope. And the telescope has not yet been built, but when built, it will be one of the largest optical telescopes in the world. There is SKA, which is already the precursor, or basically the initial telescopes have already been built. One of them is called Meerkat in South Africa. Now, SKA is similar to the GMRT which we have, but much more powerful. So it's called SKA square kilometer array, because it will comprise of two arrays. One array will be in South Africa, and it will have gigahertz observations, and another set of observations will be done at low frequency in Australia. So it will be square kilometer array, but in two parts of the world, which helps in covering a wide variety of phenomena, all the way from low frequency to very high frequency. So the SKA has been successful in including a huge number of countries, Europe and India, China, Japan, and large. We are part of SKA, and there's a lot of activity related to SKA in India. Now, the other recent collaborative project that is going on in India is LIGO. Now, LIGO, I'm sure all of you know that in, I think, 2017 or 2016, there was the first detection of gravitational waves. And a couple of scientists for India, notably Bala Iyer, Professor Bala Iyer, was involved in that. And some of the predictions of gravitational waves were done by an Indian astronomer, astrophysicist, Vishu, we call him, and he used to work in RRI and IEA. So we have a lot of connection with LIGO. And so recently, a couple of years ago, India has also joined, has made a consortium of Indian institutes all over India, and the Indian consortium has joined the LIGO collaboration. So it's nice to see, and I'm pretty senior now, and I did not see so much international collaboration when I was a student like you, and that limited the kind of science that we could do. So now I'm so happy, that to see all these international collaborations, and our government is willing to give the money for us to be also part of all these big projects. Now, the important Indian telescopes, I've just written a whole list here. One is, of course, the Hanle telescope or Himalayan Chandra telescope, which is in Leh, near Leh. Then there's Kavalur. There's the Nainital Observatory, which is called DOT, Devastal Optical Observatory. Then there is a optical observatory and near infrared also in Mount Abu, which PRL is in charge of. There are several solar observatories, but I think the best one is the Udaipur Solar Observatory. We also have solar observatory in Kodaikanal, and we have one in Goribidnu, but I think the Udaipur Solar Observatory produces more exciting research at the moment. There is, of course, the GMRT. The precursor to GMRT was the Ooty Radio Telescope. If you ever go on a holiday to Ooty, please take a diversion and go and see the Ooty Radio Telescope. It's a telescope mounted on the side of a hill, a paraboloid on the side of a hill. So it's a very interesting structure. And in the 80s, it produced a lot of very wonderful results, several of which were published in Nature papers. And the Ooty Radio Telescope was, in those days, controlled by TIFR, but now RRI and TIFR both look after this telescope. There is the Goribidnu Radio Telescope and the Hagar Gamma Ray Observatory. Now, I might have missed a couple of observatories here because, as you can see in India, now there are many, many astronomical observatories. It requires a lot of manpower to look after the observatory because most of them are located in very isolated places. So I think that, it's great that we are able to support them. Now, why is it important to have so many observatories observing the universe at different frequencies? So basically, why is multivariate observation so important? Now, it's important because when you look at a galaxy at different wavelengths or a star or some other object in our universe, you will be looking at different physics. Now, if I look at Andromeda in radio, low frequency radio observations, what I will be able to observe, as you see here, is the radio continuum coming from star formation and supernova remnants. But when I start going to, say, the infrared, I'll be looking at dust. And then in the mid-infrared, the dust will become very, very prominent. And if I go into the near-infrared, which unfortunately I didn't show here, I will get the stellar structure of the galaxy. But as we move to higher and higher frequencies, then you will be seeing more energetic phenomena. This is an optical image, and you can see the optical image looks so much different from the other wavelengths. And that's because each wavelength is looking at different physical processes. For example, the UV here, that is really tracing the star formation coming from the massive stars, not from the low mass stars, but really the O and the B type stars. So the light that you see is concentrated in these ring-like structures, which represent the spiral arms of the galaxy. Now, if I go to X-ray, and if I went to gamma rays even beyond that, what we would mainly see is the nuclear activity, because usually the nucleus is where the most energetic processes happen in galaxies. So in here, the nuclear activity or nuclear X-ray emission is possibly coming from the active galactic nucleus. Now, why do galaxies appear so bright? That may a child also may ask this question. Now, this star formation that we see is coming from the nuclear fusion processes in stars, but the star formation process itself starts from the collapse of massive interstellar clouds. The main fuel for star formation in galaxies is molecular gas. Now, molecular gas clouds are surrounded by neutral hydrogen clouds, and beyond that, outside of that, you have the ordinary ionized gas and interstellar medium. Now, so the heart of the molecular cloud will be cold because it is shielded from the UV photons by these outer layers of molecular gas and neutral hydrogen gas. Now, at sometimes this central core may become unstable and it will start collapsing. When it starts collapsing, gravitational force will make it collapse on top of itself. When the center of the cloud becomes hot enough to start nuclear fusion, that is when a star really is kind of born. Before that, when it's collapsing, it's called a protostar. But when it starts doing nuclear fusion and gives out energy, then it has become a star. Now here I've just shown you an example of a galaxy which is having an enormous amount of star formation. It's a very famous galaxy called M51, Messier 51. And what you can see are these beautiful spiral arms. The spiral arms are driven by a density wave. Just like you have sound waves, there is also a density wave which is supposed to be driving the stars and gas to produce all this beautiful light from star formation. Now, one of the reasons that this density wave may have been triggered is because of the interaction with the neighbor, M52, which is a nearby dwarf galaxy. And so you can see here, there are these pink points, pink and blue points. Those are star-forming clusters. And you can also see these dark patches. These dark patches are regions where there is only dust. There is dust, and that dust absorbs the UV photons and makes the region look dark or black. So I wanted to show this because I think everybody should know that why the galaxies appear bright. Now, star formation happens because the cloud starts collapsing on itself, but this also happens because of, on a large scale, because of cloud collisions. Now, this is an example of how this is happening. So basically, like I showed you in the previous image, that if a galaxy is perturbed, its axisymmetric distribution of mass is kind of disturbed by a nearby passing object, another galaxy, then what happens is the circular orbits of the clouds is disturbed, and this leads to cloud-cloud collisions. Now, over here is a cartoon showing that what can happen when two clouds collide. There is two clouds, the blue and the red one over here, and when they collide, there is a shock formation. And because of the shock, the gas is heated. Now, when gas is heated, then what happens is, just like when you burn a fire, it will try to cool. And when it cools, when gas cools, then it becomes gravitationally unstable. And these gravitationally unstable fragments of gas will start forming stars. And this will then appear like a cluster. So this is how star formation happens. And this is why we see galaxies as they are shown in this slide over here, why the galaxies appear so bright. Now, galaxies in our universe also evolve. They do not remain static because there is so much kinematic activity, and there is nuclear fusion, there is stars forming. So because of all this activity, galaxies will be changing with time. So this is what we call as galaxy evolution. Now, but we can classify this galaxy evolution through the following processes. The first is galaxy interactions, and the second is star formation. Now, they're both actually very connected, because when galaxies collide and merge, they can, as shown in this image here, they can form a larger galaxy. So there's a hierarchical buildup of mass in the universe, smaller galaxies merging to form bigger galaxies. Now, when this happens also, there is a lot of star formation, as shown in the image over here of R220, because there is gas in most of the spiral galaxies. And when gas is shocked, then it starts forming stars. And this star formation can again lead to the buildup of mass. So again, you will have mass buildup. So this is basically the two processes leading to galaxy evolution, which is a very important topic in studies of galaxies. Now I'll come to the second part of the talk, which is the nuclear activity of galaxies. And very briefly, we can just talk about what is the nuclear activity due to. It's basically due to two processes. One is nuclear activity is driven by star formation, nuclear star formation. As you can see over here, the bright pink spots and the heart. The heart here has also very strong, bright, luminous, compact star-forming regions. The second reason we see nuclear activity in galaxies is the accretion of mass onto the black hole. So let me just talk about the first one, the nuclear star formation. The nuclear star formation, of course, you can imagine the nucleus of a galaxy is the center of its potential. And in any gravitational system, the center of the potential will be the place where the densest accumulation of matter. Now, when matter is very dense there will be cloud collisions, and again, there'll be star formation. But then if there is some activity like a merger happening, then this star formation becomes really very enhanced. And that's when we get what is called a starburst. And so starburst actually happens mainly in cases like R220, where you have the mergers of gas-rich galaxies. However, you also have quiescent star formation in the nuclei of galaxies. In some cases, it can be also attributed to what we call nuclear star clusters. Nuclear star clusters are a bit like globular clusters in the nuclei of galaxies, but they are much brighter, and they host usually very massive stars. Now, the second reason for nuclear activity is the mass accretion onto a black hole. And I think most of you know what is a black hole, but I will mention it at the end as well. A black hole can be the end state of stars, or it can be the accumulation of many black holes to form what we call a supermassive black hole. But however, whatever its mass is, a black hole will, by its enormous gravity, want matter to fall into it. We call this accretion. Now, when mass is accreted into a black hole, all of it is not accreted. Some of it is released as energy. If you remember the equation E is equals to mc squared, m is the mass. Any mass which is falling into the black hole, if some of it is given out as energy, you can imagine that energy will be very high. And so the nuclei of galaxies which have AGN are very, very luminous. Now, I just wanted to show you the kind of the structure of an AGN. This is what we call a phenomenological model. This is from various observations over the years. People have thought that this is what is the model of an AGN, and it is often referred to as the unified model of AGN, unified model of active galactic nuclei. And what it is comprised of is the black hole here at the very nucleus. Around it, there is an accretion disk. An accretion disk is continuously being driven by viscosity, and therefore some mass falls into the black hole. there is surrounding the black hole these broad line clouds. We call them broad line clouds because they are compact, dense blobs of plasma which move so fast that when light falls on them, they keep on Doppler broadening the light. So the broadline cloud, the broadline refers to the broadening effect that these clouds have on the light coming from the nucleus. Now, beyond that are the narrow line clouds. The narrow line clouds are a little less dense than the broad line region clouds. And so you can see over here, they look a little bit bigger. And the narrow line clouds, because they're not in the heart of the deepest part of the potential, they're not moving that fast, so they cannot broaden the emission lines that much. So they are called this is called the NLR region. Now, surrounding all of this is what we call a torus. Now, the torus is it's like a vara, and it is composed of dust and basically ionized plasma and dust. Now, you could be looking at an AGN. Either you can look down through the hole, so you can be looking, down through the hole in the vara or the donut, or you could be actually looking through the torus. Now, depending on what your angle is of looking at the AGN, you will see the AGN in different ways. If you are looking through the torus, then the dust will polarize the light. So you will say that the nucleus is giving out polarized light. But if you're looking through the top, through the hole, then you will not be polarized so much, and therefore you will see a very broad emission line because you will be going through, your line of sight will be going through all these BLR clouds. So this is called the unified model of AGN because it's telling us, the theory is telling us that depending on what way you're looking at, what angle you're looking at the AGN, depending on that, you will see a different kind of emission, but the model is the same. I'll go a little fast now because I think I'm taking up a lot of time. Since I mentioned already AGN, I'll just show you a picture. This is a work that I did with my previous PhD student, Jyoti Yadav. And here she detected AGN in 1 and 2 nuclei. So it's a dual AGN, but she also detected a third AGN in this small galaxy over here, which is being accreted. So this was an example of a triple AGN system. You do see double and triple AGN, but they are rare. You see them in mergers or in small groups. Generally, you will see AGN in, I think a large fraction of galaxies, at least 20 to 30% of galaxies have very active AGN. You have to remember that a galaxy will have an AGN, active galactic nucleus, only when the black hole is accreting. So sometimes there is a black hole in the center of a galaxy, but it's not accreting mass, in which case it's silent. So in those cases, it's very difficult to detect the black hole. Now, in our galaxy, the Milky Way, our black hole is fairly silent. It does not have an accretion disk, which means it is not continuously accreting mass. So we don't see, a lot of phenomena associated with AGN, such as jets or variability so much with our Milky Way nucleus, but we do see it in all nearby galaxies. Now, for example, in this galaxy 773334, which I studied with Jyoti, in the J band, you can see very clearly that there are 3 bulges, 1, 2, 3 in the 3 galaxies. And you can see in UV that the star formation is present in the rings, in both the galaxies. When you look at the UV, FUV, there is even more emission, which is associated with a kind of a tidal tail over here. Now, all of this information, because it's multi-wavelength, it helped us to understand this merging galaxy system, that it was composed of 2 galaxies, disk galaxies with tidal arms, and a third galaxy, which one of the galaxies had already swallowed and produced a triple AGN. Now, over the years, we have also, with my students, I've been looking at the radio emission from these galaxies. And this is a very nice source that we studied both with the GMRT as well as with the very large array telescope in New Mexico. So what we observed in this galaxy is that it has radio emission, but you can see it has an S-shaped emission structure. Now, this S-shaped emission structure is what we call as a precessing radio jet. And a precessing radio jet is often the result of two black holes going round each other. So we did a lot of very, exciting observations, but we found that the supermassive black holes are way in the nucleus, and it was not possible to distinguish with our VLA and GMRT observations. However, we were able to look at another galaxy where we saw the nuclei. This is Markarian 212, and both of the nuclei are AGN. This is 1, and the circle here, circle 1 and 2, denote the two nuclei. So this is a dual nuclei system, and both are accreting, so they are both AGN. So this is a dual AGN system. What was nice about this observation, though, is that we were also able to see the star formation associated with the two nuclei coming together. Because whenever you have two nuclei merging and there is gas in the system, there will be a spiral structure associated with the merging. And this spiral structure, in some cases, can give rise to star formation, which we can see very nicely in this observation. Now, I told you about AGN and galaxies and AGN, and now I thought I will end my lecture by discussing the black holes. I mean, I am not an expert on black holes. I do observations of accretion onto black holes, but I really do not know the details. But let me just share with you what I know. Now, there are two ways to look at a black hole. The classic definition of a black hole is a region in space-time where gravity is so strong that not even light can escape. Now, if you remember from your class 12, when you did the satellite problem, then you had the escape velocity from a planet, from the Earth, which is v squared is equals to gm by r. Now, suppose that we have the mass becomes so large that the velocity has to become larger and larger. The maximum velocity that you can get, escape velocity, is the velocity of light. So that is the definition of the black hole. C squared is equals to gm by r. That kind of defines the classic definition. Now we also know from Einstein's theory of relativity that nothing can move faster than light. So this is kind of the definition, if we look at it from classical mechanics, what is the black hole. Now, if you look at it from GR, then you have to think of it as a singularity. And so there you have a kind of a bifurcation in the definition. You have the mathematical definition and you have the physical definition. The mathematical definition is that it is a singularity in space-time where the solution of the gravitational field cannot exist. And so there are a couple of radii which are associated. The one that is often used is called the event horizon. And we have to remember, in whatever definition we use, that the gravitational force around a black hole is so strong that it distorts space-time around it. This is the mathematical definition, which will come from the general relativity equations, but there's also a physical definition which you can think of. The physical definition is related to that they are the end state of stars. So massive stars become supernova, and if they are very massive, they will leave behind not a neutron star, but a singularity, which is a black hole, because it keeps collapsing on itself since it is so massive. So I think there was a movie associated with this, but this is just the image to show you how a massive source can distort the space-time around it. You can see here, this is the most massive object, and therefore it is creating the most massive distortion, whereas the smaller object over here is not creating so much distortion. So I think in popular literature, there's been a lot written about this, but one of the nicest experiments, I think, was the bending of light around the sun. And this was an experiment done by Eddington more than 100 years ago. And that is, I think, if you have time, you can read about that experiment. Now, the centers of all galaxies are thought to have black holes. If they don't, if observations show that they don't have black holes, it means that the black hole was kicked out of the nucleus due to some activity. There are kind of two types of massive black holes. One is called the supermassive black hole, where the black hole mass is more than 1 billion times the mass of the sun. So greater than or equal to 10 to the power 6 solar mass. Then there is the smaller black holes called the intermediate mass black holes, which are found in the centers of dwarf galaxies and irregular galaxies, basically much smaller galaxies. They have masses of 10 to the power 4 to 10 to the power 6 solar mass. So here I've just given you a picture of two types of galaxies. If I looked at them, I would guess that the elliptical galaxy probably has a more massive black hole than the spiral galaxy. But of course, it depends upon the mass of the elliptical galaxy as well. Now, how can we detect nuclear black holes? So this is actually a repetition of the previous slide, because I just wanted you to remember that one of the only ways in which we can detect a black hole outside of our galaxy is through accretion. So if a black hole is accreting mass, some of that energy mass will be given out as energy, and that energy we will be able to detect. So this is one of the main reasons why it's important to study AGN, because that's one of the only ways in understanding the distribution of black holes in our universe. Now, there is also other two ways to detect black holes. One of them is by observing the mass, the stellar orbits of stars around the black hole, because the gravitational force of a black hole will distort the velocities and motion of the star, the orbits of the stars. So that's one of the ways. Another way, which I'm not covering in this talk, is by observing the maser or the microwave laser emission coming from clouds which are very close to the nuclei. And so I will talk about imaging because there is, due to the lack of time, I'll just talk about another one of the methods, and that is the imaging of the massive black hole in nearby galaxies. Now, this is the third method I mentioned. Studying AGN is one of the ways of studying black holes. Then looking at the motion of stars around the black hole. Basically, that is called the stellar dynamics method. Now, the third method, which has come up in the last decade, is actually imaging the emission coming from mass falling into a black hole. Basically, if there is an accretion disk, then the accretion disk will give out electromagnetic radiation, which is usually synchrotron emission, when matter falls into the black hole. Now, to understand this further, I've just made a cartoon here. You can see here, there are a couple of radii here. One is the singularity over here, and the second is the event horizon. So the event horizon actually has a value R equals to 2 gm by c squared. Now you notice m, the mass of the black hole is here. So if the galaxy is very massive, usually it will have a massive black hole, and this radius will be quite large. Whereas if the galaxy has a lesser massive black hole, it will be much smaller. Now, when matter falls into the black hole, some of it is converted to energy, And that energy can heat up the gas, the plasma around it, and give out synchrotron emission. And this synchrotron emission can be detected by telescopes, by radio telescopes. So this is basically like a cartoon about how the black hole forms, but the light that we can see will be detected with the radio telescopes. So let me just quickly go through this, how we are making the black holes. The first step is to form the first stars from the hydrogen helium in the early universe. Then these first stars can become supernovae, and then when the really massive ones are collapsing, they will form the first seed black holes. And then these seed black holes will keep on growing due to the galaxy mergers and the accretion of mass. So this is how the black hole forms and grows. Now, the next few slides, I'll talk about how we are detecting them using the effect of the gravity around them. As I mentioned earlier, there are several ways to detect the black hole in the center. One is, of course, detecting radio waves from the synchrotron emission. But over here, I've also mentioned another few methods. One is when gas clouds near the center of the galaxy are swallowed, tidally disrupted. Okay, when there is tidal disruption of stars, then X-ray emission is also given out. And the Fermi bubble, there can be some remnant nuclear activity, which will be like bubbles near the center of the black hole. Now, our galaxy does not have an active galactic nucleus. It does not have a nucleus, black hole, surrounded by an accretion disk. So that makes it very difficult to detect it actually, because the synchrotron emission, radio emission is not going to come out very much. But if we have periodically, if we are able to see tidal disruption events or flares near the center of the galaxy, we'll be able to detect that in radio frequencies and observe it. Now, as I mentioned earlier, another way to detect the black holes is to look for the motion of stars, the stellar orbits near a black hole. This was the method that was used to detect the black hole in the center of our galaxy. And the two people who did it, one person in Germany in Max Planck, Genzel, and the other person, Andrea Ghez, they were two separate groups and they got the Nobel Prize in 2012. What they did was they tracked, and you can see over here, all these orange blobs. These are stars, which are imaged in near infrared using a special technique called spectral interferometry. And these, if you can keep on imaging these stars at regular intervals, what you can do is recreate their orbits, as you can see over here. This is like an orbital structure, these rings. Now, if you have the orbital structure of anything in a potential, you can actually use simulations and numerical methods to recalculate that potential, which will give you the mass. So this is what they did. They tracked this motion of stars near our galactic center, and they worked back and got the mass of the black hole in our galaxy center, which is 4.2 into 10 to the power 6 solar mass. The third method is to actually image the light coming from around the black hole, and this is an artist's impression of what can be happening around a black hole which has an accretion disk, which you can see over here, pointed over here. Now, if there's an accretion disk, then mass will be falling at regular intervals from the event horizon into the black hole, and some light will be given out. Some electromagnetic radiation will be given out. There may also be jets which are shown over here, and the jets are coming from the inner edge of the accretion disk. Now, all of this emission can be detected using radio waves, and it was done. It's been done for the past 20 years by the Event Horizon Telescope (EHT) consortium, which is basically an array of telescopes all over the Earth. These are radio telescopes distributed all over the Earth. And you can see over here that the original detection of the black hole in the nearest elliptical galaxy, M87, was done by so many telescopes. There's 5, 6, 7, 8 telescopes all over the world. Now, the resolving power of a telescope, if you remember the double slit experiment, it is given by lambda by d, where d is the separation of the two slits. So if d is made very, very large and lambda is also made small, then we could have a very good resolving power. So this is the aim. The aim of this telescope is to use millimeter waves, which is a very high frequency and therefore a very small wavelength, and use very large distance separations of the telescopes to get a very good resolving power, which can then be used to image the light coming from the nucleus of M87. Now they went after M87 because M87 is the nearest AGN in a massive galaxy. M87 is the center of the Virgo cluster. So it's the center of a very deep potential. It's a very massive galaxy with a very massive black hole. And this is a cartoon of all the steps that was done. Okay, so let me just go through this. First of all, the data from all the telescopes had to be carried. It had to be carried and then correlated by a whole bunch of supercomputers and very smart computer engineers. And then after that, the data was, stacked, and then image reconstruction using Fourier analysis was done. And they got 3 images, 1, 2, 3, and that is the final image, which looks a bit like a donut. So the first one, as I mentioned, the first EHT experiment was centered on the M87 black hole, which is a very massive black hole, 10 to the power 9. Sorry, I've written 8 here, but I think it's 9. 8 or 9 times the mass of our sun. And here is this is just a kind of a cartoon that shows you how they were collating so much data to get finally the mass. Now, this image here is showing you the supermassive black hole in our galaxy, how that was imaged. For example, over here, this is how we see it in the optical light. This is how it looks in radio. And then in radio, with all the flares, it was observed for a long time to get this image, which looks like a donut with bright hotspots over here. So this is a comparison of the black hole in M87 with our galaxy. As I mentioned earlier, M87 has a very massive black hole, which is close to 10 to the power 9 solar mass. Our black hole is a few times 10 to the power 6. So it's about 1,000 times more than our black hole. So correspondingly, the black hole, if you can see here, is very small in the image of M87. Now, EHT is doing a lot more monitoring of nearby galaxy nuclei. And I think within a year or two, we should get more results about the black holes in nearby galaxies. But as of now, they have released only their results on M87 and our galaxy. So I will stop here. This is my summary. I hope, later on you will remember that galaxies are large collections of stars and multi-wavelength observations are very important. Galaxies are classified. They are classified using the Hubble sequence, and it's based on bulge size and spiral structure. The nuclei of galaxies all contain supermassive black holes. Of course, the smaller galaxies have intermediate mass black holes. Now, the stars and gas near the black hole is affected by gravity, and that can help us image the black hole because we can look at, first of all, the motion of the stars around the black hole. And secondly, we can look at the accretion of mass from the black hole close to the black hole. So though both these things can help us understand the mass of the black hole and the energetics near it. I think I will stop here. I think I've been talking a long time. So Adil, I think I'll stop and take questions.
So Q&A session. I think we can go to the Q&A session. Adarsh. So I would like to invite Gautam to lead the Q&A session. Gautam.
Okay. Am I audible?
Yeah, you're
Yes.
audible. Yes.
Okay, ma'am, the class was so good. And we have got so many questions from our students. So the first question is from Devi K. Kumar. How do astronomers determine the distance to galaxies, especially very distant ones?
Okay, so that's a nice question. So galaxies give out light, optical light, and that light is often can be an emission line. Now, if that emission line is Doppler shifted, that Doppler shift, or what we call the redshift, delta lambda, can be used to find out the redshift of the galaxy. Now, you had mentioned that there is, I think Jayant Murthy talked about our expanding universe a long time ago. So there is an equation which is called the Hubble's law. And the Hubble's law states that the velocity of any recession velocity of any galaxy is proportional to its distance from us. So V is equals to h0r. So if we know the recession velocity from the Doppler shift, delta lambda, so basically delta lambda by lambda is equals to V by C. Then we can use that V to find the distance r using the Hubble's equation V is equals to h0r. So these two equations can help us determine the distance of the galaxy, but we have to have the Doppler shift, which we can get from spectroscopic observations. I hope that was okay.
Okay, ma'am. I think it's a good answer. Moving on to the next question. It's from Adil Brajesh. What is the largest galaxy that ever found?
The largest galaxy? I don't think I can say exactly the largest galaxy, because every day new galaxies are being discovered by the JWST. But I remember there was a low surface brightness galaxy called Malin 1. And for many years, that was one of the largest galaxies that we know. You have to remember that when we are looking at the universe and looking at the size of the galaxy, if it's very far away, we often cannot, it becomes very dim. We cannot see the full galaxy. So if you look at the local universe, the largest galaxy was called Malin 1. But there are, nowadays I've heard that there are more larger galaxies. They are often termed as monster galaxies because they're very large. But it's still not clear whether there is a lot of extinction, dimming of the galaxies because of distance. So I think that is it's a question that is time variable. If you ask someone, I'm saying Malin 1 now, but if you ask someone maybe 2 years later, there'll be another galaxy, which is the largest galaxy.
Okay, ma'am. The next question is from Shivapriya.
Uh-huh.
What are the skills I need, or what should I do now to become an astrophysicist in future?
Okay, I think the first thing you need to do is, well, the first thing, of course, is motivation. You have to be motivated. But a background in physics and maths, I think it will be most important, because both are required to study galaxies and basically to be an astrophysicist. Physics, maths, and to some extent chemistry. There is also another branch of astronomy that is coming out now. It's called astrobiology, where it is related to finding life outside our own Earth, planet Earth. And it's becoming relevant now because a lot of exoplanets are being discovered, and people are saying some planets are similar to our planets. They're called the Goldilocks planets. So physics and maths is essential. Chemistry and biology is optional. If you have some background in those, it will also be very good. I think this is what I could say.
Okay, ma'am. Thank you. The next question is from Adil Prajesh. In future, Andromeda and Milky Way will collide. Is this dangerous in any way?
No. This will happen many millions of years later. In fact, one small galaxy, the Sagittarius clouds, LMC and SMC, are already falling into our galaxy. But even that will not cause any problem for the next more than a million years, few million years. Yes, but they are approaching one another, the Andromeda and Milky Way. That is true.
Okay, ma'am. The next question is from Abhiram Ranjit. He have two questions. The first question is, will ISRO launch AstroSat? And the second question.
Oh, okay. No.
Do I need second question? Or?
Yeah. Second question is what?
For studying the celestial bodies, including galaxies. Sorry, ma'am, it's a combined question. Sorry. Will ISRO launch AstroSat 2 for studying the celestial bodies, including galaxies?
Oh, AstroSat 2. I just heard AstroSat. So, no, I haven't seen any plans to launch AstroSat 2. See, AstroSat 1 has been successful, especially the UVIT is very successful. And there were some follow-up proposals. But right now, no, I don't think there's going to be an AstroSat 2. If there is going to be some follow-up space telescopes, it will be probably on separate wavelengths. It will probably be one launch, which I think is nearly confirmed, Daksha, is to study the transient objects in the sky. So AstroSat will not be repeated, but I think some other wavelengths they will launch very soon.
Okay, ma'am. The next question is from Parvana CS. Could you please explain how we capture or create complete images of the Milky Way?
Complete images, huh? So that's quite a broad question because we capture images at different wavelengths. Using the optical telescopes, we can get the optical images, and radio, we can get the radio images. Now, all of these are electromagnetic wavelengths. And one thing that complicates the obtaining images of the Milky Way is the fact that we are residing in the Milky Way. So that makes it slightly difficult. So we have to have the kinematic observations as well. Basically, not just the spatial position of any star, but also the kinematic information, how they are moving. So the fact that we are inside the Milky Way makes it difficult to image the Milky Way fully. But we have another advantage. There are many galaxies in our universe. So people have observed several galaxies which are very similar to our Milky Way. So those galaxies have helped us to understand, to image, in some sense, our Milky Way galaxy. So I hope that has answered the question.
Okay, ma'am. Thank you. Moving on to the next question. It's from Adidev. How do the bars form in paired spiral galaxies? Do they form differently as compared to regular spiral galaxies?
That's a nice question, especially because I work on these barred galaxies. So bars are elongated features in the centers of galaxies, and they form due to a special instability which is present only in self-gravitating disks. So the disks of stars under their own under their own gravity, they will be rotating in differential rotation, but this is not stable because the whole system will want to collapse on itself. So to stabilize the system, the galaxy spontaneously forms a bar instability. So this elongated bar. Now the bar, what it does, it is symmetrical. So it kind of redistributes the angular momentum. And the bar, however, cannot form if the surface density of stars is very low. So if the system doesn't have very good gravity, doesn't have a lot of stars, then it possibly the bar will form, but then it will dissolve. Another reason for forming bars is the velocity dispersion of the stars. If the velocity dispersion of the stars is very high, if the system, we say it is kinematically hot, then it does not allow the bar to form. But generally, any self-gravitating disk of stars will want to form a bar spontaneously as a gravitational instability.
Okay, ma'am.
Is that okay?
Moving on to the next question is from Padmanabhan.
Pardon?
No, ma'am. It's the next question is from Abhiram Ranjit. What will be the speed of particles inside the accretion disk of a black hole?
Oh, okay. So it's a nice question. When we observed using radio observations, using the GMRT also, we found that the speed of particles near the black hole, near the accretion disk, can be just a fraction of the velocity of light. So I think like 0.1 c or even 0.5 c. I mean, that is the kind of speeds you get very close to the black hole. Now, the radio jets that are coming from the black hole, I think those are the ones that can give you some information about the velocity in the accretion disk. And those come, when they come from the black hole, they have velocities ranging from 0.1 c to 0.5 or 6 c. So velocities of gas and stars inside the accretion disk must also be very close to the speed of light, must be very moving very fast.
Okay, ma'am. Thank you. The next question is from Arya Shiju. What are some recent discoveries in AGN research?
Recent. So I think one of the discoveries, I'm not an expert, but I think the two things which are very important is using AGN to measure the mass of the black hole. That has been, in the last 20 years, that has been a very important understanding of black holes. And another thing is the variability of the AGN. So the AGN are known to vary sometimes on the scale even of days. And that is very remarkable because that variation is indicates that things are moving very fast there, close to the speed of light. So AGN variability, then AGN, using AGN to find the mass of the black hole. These are some interesting results. The mass, AGN, using AGN to find the mass of the really smallest black holes has also become very popular. People have found that there are intermediate mass black holes associated with AGN in dwarf galaxies. That is a recent topic. The JWST has also found a lot of interesting, activities around phenomena around AGN. The AGN winds, outflows and winds coming from AGN, and how they can be used to enrich the circumgalactic medium around galaxies. This is also now a very hot topic. And I think outflows, AGN outflows, AGN black hole mass relation, AGN bulge coagulation. These are the recent results that have come out in AGN studies.
Okay, ma'am. Thank you. So the next question is from Adidev. Does the Parker Solar Probe experience any time dilation when it flies by the sun? Or is the sun's mass not high enough for it had any sizable effect on the space-time?
Oh, that's an interesting question. I don't know for sure, but my impression is that the Parker probe will not go that close. So to have some effect, space-time dilation effect, or basically to experience the curvature due to gravity near the sun, you'd have to go very close to the sun. I don't think, I'm not sure that whether the Parker probe will go that close, because if it does, I mean, it may get burnt, basically. It may get destroyed. So my naive answer to that is no, nothing. It will not be able to experience the time dilation.
Ma'am, the next question is from Adil Prajesh. If there is gravity, the time will bend. If there is any kind of repulsion or some thing happened, I mean something.
Oh, so basically the time and the effect of gravity on time, no?
I don't understand, Adil. Adil, could you please clarify that?
Hello,
Yes.
can you hear?
Yes, I can hear.
My question is actually, if there is a gravity or attraction, the space-time will be bent, you know.
Yes.
And then alternatively, if there is any kind of repulsion or something happened, what will happen to the space-time?
Oh, I don't think so. Then space-time curvature, yes, will be affected. But as of now, nothing can. There is no repulsive force that can affect space-time. I mean, that kind of force has not been discovered because it has to be very large. See, gravitational force is a very strong force and it's attractive. To have a repulsive force on that scale, I think will be difficult. And I don't know actually if there any such force exists. Sorry, I cannot answer the question much better than that.
Okay, thank you.
Okay, ma'am, moving on to the next question. It's from Abhiram Ranjit. If the nucleus of our Milky Way and the Andromeda Galaxy, our supermassive black hole, Sagittarius A star, it will become a quasar.
A quasar. So a quasar. So as I mentioned earlier, our black hole is silent. That means it is not accreting mass. If it's not accreting mass, then it won't give out light. So now quasars are known to have accreting supermassive black holes, and that makes their light not only very bright, but also it makes it variable with time. So from our nucleus, we see some variability, but we don't see that kind of bright light. So in order for it to become a quasar, we first need to have an accretion disk. An accretion disk has to form, and that will possibly form when there is a merger with a larger galaxy, with a companion galaxy.
Okay, ma'am, thank you. The next question is from Adidev. In the extremely distant future, could it be possible for a black hole to die out via Hawking radiation?
Hawking radiation is known to affect very small black holes. It can make them evaporate, but a very massive black hole, for example, our black hole is 1 million times the mass of the sun, it cannot affect. It won't be significant enough to affect it. This is my understanding of it.
Okay, ma'am. The next question is from Abhiram Ranjit. EHT is now active in imaging supermassive black holes.
Yes. So it is imaging supermassive black holes. As I mentioned, it has done it for our galaxy and M87, as I showed in my slide, previous slide over here. And now it is also doing several other galaxies. And I think very soon in the future, within next 1 or 2 years, they will release more data on nearby galaxies. But it is doing many galaxies, yes.
Okay, ma'am. Thank you. The next question is from Nidasri. Are all galaxies expected to have had nuclear activity at some point?
That's a nice question. Actually, yes, because matter, when galaxies are not alone, they are not isolated. They would interact with other galaxies sometime in their life. So if that happens, then there will be some mass infall into the nucleus, and this should cause an accretion disk. But there are some, in fact, I think some 70 to 80% of galaxies show no activity from their nuclear supermassive black holes. So there is what we call an AGN cycle. And in that AGN cycle, there will be accretion disk activity with the black hole. And then it will quench itself, it will kind of push out all the gas using outflows. So it will die just like a fire dies. Or it will, I guess it will have another merger and the accretion disk may get destroyed. So these are some of the options. But AGN cycle is something that a lot of astronomers talk about nowadays, and it indicates that AGN are not always, the supermassive black holes are not always active. Is that okay?
Ma'am.
Yeah.
Okay, ma'am. Thank you. The next question is from Avani Chandra. What is the role of dark matter in the formation of supermassive black holes?
So that's a good question. So we know that the dark matter in the present theories about structure formation of our universe, dark matter formed these potential wells, and matter collected in these potential wells, and that matter became galaxies and the structures that we see. Now, in the center of these potential wells, there are also supposed to be primordial black holes. Now, these primordial black holes, some people say that they could be formed using dark matter, or else they could be formed in parallel with dark matter, or even before dark matter wells were evolved. So I think it's still a matter of research. It's not clear that how the supermassive black holes were formed inside the dark matter potential. It's not clear, I think.
Okay, ma'am. Thank you. The next question is from Pradeep Kumar. Is it true that the black holes are the main reason for the collision of stars and even for the creation of our moon? I mean, that all the possible alteration in galaxies are due to the black holes.
No. Black hole is just one aspect of a galaxy, and a black hole's effect does not extend for beyond, a very small fraction of a galaxy.